Okay, so we just saw about multilayer, and now let's talk about the capacity of multilayer. Means we saw that there were certain kinds of functions that you couldn't model, lots of functions that you couldn't model with a single neuron. So what if you add more neurons into a layer? What can you do? So we saw that one neuron can create a surface like this. So if one neuron can create a surface like this, if we had a different set of weights and so on, or a different set of weights and a different bias, we could create a function like this. So if we have two neurons, one which generates this function and another which generates this function, then we could take the difference between these two as a linear combination because remember we're going to just be adding what comes out of here times some weight and what comes out of here times some weight. So that's basically just a linear combination of these two. So one such linear combination would just be the difference between these two. So if we took the difference between these two, you can probably see that you will generate this shape here. In other words, it's kind of ridge. So let's see if I can show that a little bit more clearly. So this one generates this picture. So it's the same picture we just saw. The fact that this is green and blue is not relevant right now. It's the same height here. And this one, the fact that this is red and green is still not relevant. It's still the same height down here and then jumps up here. So if we subtract this one minus this one, then in the region where it's red, we're going to have 0 minus 0. We're talking about the height. So that's going to be still 0. And then it's going to jump up here. This part is going to jump up here, and this is still going to be 0 over here. So it's going to be like 1 minus 0 is still going to be 1. But then over here, this part jumps up to 1, so we get, when we do the subtraction, we're getting 1 minus 1. It goes back down to 0. So we can get this kind of ridge here. And then if you take 4 of these, and now we're not assuming that they're just completely like a step function, there's some gradual increase, like more like a sigmoid function. Anyway, if you add all these together or add and subtract these, you could create like a kind of a bump here. Okay? So we could create this kind of bump. And then if we add in even more neurons, let's see, do they have, no. But if you add in even more neurons than just 4, like you add another 4, you could create another bump somewhere else in this, and so on. So you could generate all these kinds of bumps. And then, if you're doing a binary classification, for example, that means you'd be basically cutting the surface at a certain level here. And in other words, you'd get a classification surface that could look something like this. So you could generate a classification boundary or decision boundary that looks like something like this. So this would be R1 and this would be R1. They would be separated, but still these would. So basically you could get a very complicated decision boundary using this. And in fact, there's a formal proof that says that a neural network can be a universal approximator to basically any kind of decision surface or any kind of function. So a single hidden layer neural network with a linear output unit can approximate any continuous function, has to be a continuous function, arbitrarily well given enough hidden units. And this applies whether you're using a sigmoid function, or it also applies if you're using a hyperbolic tangent, and there are other functions that it also works with. So that gives us a lot of hope for for using neural networks. However, this is a good result, but it doesn't mean that there is a learning algorithm that can find the parameters. There are parameters, doesn't mean you can find them. In other words, we haven't talked about how to find the parameters, but we use basically back propagation, and we use most of the time we use what's called the gradient descent method. But anyway, we haven't talked about that yet. But that's not going to necessarily find the parameters. I mean, it might, but it might not. So there's a whole field of research that are looking for other or better learning methods. In other words, learning methods means ways to fine-tune the parameters, or ways to identify the parameters which will approximate any particular function.